This is problem 16-5. A 450-pound crate, 18 inches wide by 45 inches tall, is sitting on the back of a truck as shown in the figure below. The truck is traveling at 65 miles per hour when the driver suddenly applies the brakes. Determine the minimum distance required to stop the truck without causing the crate to tip over, and the minimum static coefficient of friction required between the crate and the truck to prevent the crate from slipping. Okay, so there's a lot to unpack here. One thing is that they give us the width and the height of the crate, and they don't say explicitly, but you should assume that there's a uniform density. Therefore, the center of gravity is right in the middle, and that will be important. Okay, so they want us to find the minimum distance required to stop the truck, so some distance d, right? And then the minimum static coefficient of friction between the crate and the truck, so a mu s. All right, we have got to figure out what to do to solve this problem, and the math is obviously where we're going to go with this, so let's take a look. Okay, so let's start with some of our knowns. Well, we know we got a crate here. And let me redraw the dimensions so we don't forget what they are, 18 inches and 45. Okay, now I said that we should assume that there's a center of gravity right in the middle. We know that the mass of this crate is 450 pounds. Oh, sorry, that's not the mass, that is the weight. Okay, so let me make sure and rewrite that. And the truck is traveling at 65 miles per hour. So we'll go with that. Initial velocity is 65 miles per hour. So they want us to know some sort of distance d that the truck has to travel. And then they also want to find a mu sub s, the coefficient of static friction between the crate and the truck. All right, well, first, let's do a free body diagram of the crate and see what kind of values we get. So we know that we have a weight, and we are given that is 450 pounds. We also know that we have a normal force, and then there's going to be some sort of a frictional force. Now, it doesn't ultimately matter which direction we draw this vector F for the friction. I mean, we know that the friction is at this location along the bottom of the surface of the crate. But we could draw the friction going to the right, we could draw the friction going to the left. If we draw the arrow in the wrong direction, we'll just get a negative number. It's not a big deal. But let's take a second and think about which direction this friction probably is actually pointing so we can try to get a positive number. So if the truck is moving in this direction, but is then trying to stop, that means that there is a force imparted on the truck in that direction. If the crate is trying to continue moving to the right, then that means in order for the crate to stop, there also needs to be a force pointing to the left. Therefore, the friction is the thing stopping the crate, the friction between the crate and the truck. So the friction has to be pointing to the left in order to be slowing the crate down that we have been told is moving to the right. Okay, so we are pretty confident that we are going to get a positive number if we draw the arrow to the left. All right, that also means, and this is not quite as vital, but then there's an acceleration in the x also to the left. Okay, so that means we can do some of the forces in the x, some of the forces in the y, and because we're dealing with rigid bodies, some of the moments, and we're going to go ahead and pick the point G, the center of gravity. All right, so some of the forces in the x, what is that going to be? Well, I only see a force to the left, and that's the friction, so negative F equal to the mass times the acceleration. Well, the mass is going to be the 450 pounds divided by the acceleration due to gravity, and then the acceleration in the x direction. So now we can do some of the forces in the y, and that is going to be the normal going up, And then the weight coming down, so minus 450 equal to the mass times the acceleration in the y, but we do not expect this crate to lift off the ground or to pass through the bed of the truck, so acceleration in the y will be 0. We'll have a 0 term on that side. Okay, finally, the moments about g. Well, the normal force, this is, let me get rid of this acceleration. That was just for me talking. Okay, so we need an idea where this normal force is actually acting, because we care, since the normal force is perpendicular, or going straight vertical in this case, then we need to know how far in the horizontal from the center of gravity the normal force is being applied. Well, again, it's like problem number 2. The minimum distance that we can, the crate is not going to move, and it's also not going to tip over. So it says determine the minimum distance required to stop the truck without causing the crate to tip over in the parentheses. So we're back to that scenario again, where we basically have the crate about to tip. So I'm going to move the arrow, but it doesn't quite tip, which means the normal force is actually right at the corner. The corner of the crate is the contact point that is basically taking all the load, because the rest of the bottom of the crate is right about to lift off the ground, off the bed of the truck. Hasn't yet, but it's just about to. So that puts the normal force being half the distance away from the center of gravity, which is 9 inches. So that puts us at the normal. Ignore the fact that I use red. Let's just go with this. Okay, the normal times the distance of 9 inches, okay, minus, and you'll see why I put minus here in a second, the friction, which is going to be halfway down from the center, halfway. The center of gravity is halfway down the box, and the force is all the way at the bottom, is what I mean to say. So 22.5 is the distance. That's half of 45, and then times force F. And the force is trying to rotate around in the clockwise direction, so that's why I have the negative. Okay, the box is not actually going to tip over, so there will be no angular acceleration. All right, we have 1, 2, 3 unknowns and 3 equations. Therefore, we can solve. So the normal force is equal to 450 pounds. The frictional force is equal to 180 pounds. And the acceleration in the x is equal to negative 12.88 feet per second squared. Okay. We're still not done with the question, though, of the distance. Okay. Now, one thing, though, is we know the friction force now, and we also know the normal force. Therefore, with this maximum braking that can happen without tipping the crate over, we can now find out what the necessary coefficient of friction is to keep the box in place. Now, this isn't the actual coefficient of friction. We don't actually know the coefficient of friction. In fact, you can only get the coefficient of friction basically from experimentation. So, but we at least know what it has to be at minimum, because in our scenario, the crate didn't move during the deceleration of the truck. So that means we can take our friction force equal to the normal force times the static coefficient of friction, solve for mu sub s. All right, so mu sub s is the friction force of 180 divided by the 450, which is equal to 0.4. All right, remember that there's no units for coefficient of friction. It is just a ratio. All right. Well, I mean, we at least got the coefficient of friction, but we still haven't found the minimum distance required to stop the truck. Okay, we just created the scenario where the truck is stopping and the crate is about to tip over, but doesn't actually tip over. And then we were able to find out also that the crate doesn't slip because we said it didn't slip, and mathematically, and then we found the coefficient of friction. So we're kind of working the problem in the wrong order here. But what we need is we need a relationship between the velocity and the position of the truck. Okay, so we can, since we know the acceleration, we can then use the chain rule to create a version of acceleration that is a function of velocity and position. Okay, what do I mean by that? We've done this a couple times, but let's look at it because it makes maybe just a little bit extra sense why this chain rule is being used. So we know the acceleration is the change in velocity over the change in time. Okay, and then if we use the chain rule, we can take dv and we can take dt and we can multiply by 1 being dx over dx. Okay, so dx over dt is velocity. So this becomes a velocity times dv over dx because we can. And then that means we can multiply the dx over. So we have a dx equal to v dv. And then if we integrate both sides, we will end up with the actual acceleration, which is a constant, so it'll be the negative 12.88 integral of dx, which is just going to be x plus c, right? Okay, and then we also have the integral of v dv, which that is going to equal v squared over 2. Okay, so let me just rewrite the problem one more time with, now we have negative 12.88x plus c equal to v squared over 2. There's 2 plus c's, but you can combine them into 1 plus c. So how are we going to find this plus c? Well, we do know what basically the initial condition of the velocity is. We were given it here. So therefore, we can solve for c. If you solve for c, then you will end up getting the value of 4,544.2 feet per second. Okay. By the way, when you plug in the 65 miles per hour, you need to convert to feet per second. And that is the initial velocity equal to 95.33 feet per second, just so that way you can be sure. All right, so there is an x. Oh, I'm sorry. This is also when x is 0. I forgot to mention that, okay, because this is the initial position and the initial speed. So therefore, now we know what c is, and we can rewrite this function as being negative 12.88. Well, I can put the plus c over here, 4,544.2 equal to, sorry, there's an x, negative 12.88x, v squared over 2. That is the function. Sorry, it's a little messy here. All right, and what are they asking us for? They're asking us for the distance required. Well, if we know that this is when the velocity finally equals 0, then we can find the distance. We know the initial velocity basically is this initial condition. It's the 2 c's added together, so that's why it's kind of a weird number. But if we want the velocity to go to 0, then that means this whole term goes to 0, and we can just solve for x. Well, x is equal to 353 feet. So let me just highlight this one more time, that the reason we did the chain rule is because we know, this is just like first semester calculus, that the acceleration is the change in velocity over change in time. Okay, we do the chain rule because we need our acceleration to have some velocity and distance terms associated with them. That's why we do dx over dx. Okay, so let me rewrite again that final equation. 4,544, I'm just going to round off, minus 12.88x, a position, equal to a velocity squared over 2. So we took our acceleration, that is velocity as a function of time, and we ended up with an equation that has position and velocity. This was derived from an acceleration value. So this is describing our truck's or crate's acceleration, but with distance and velocity terms. That's why this is so convenient. Okay, so that's the reason for doing the chain rule, because this is still talking about the motion of the truck and the crate. This is still the acceleration equation. It's just been changed in form that now it can be described using a position and a velocity value. And that is how we got to the point where we were able to answer the distance that was needed to stop the truck. And we made this velocity term 0 once we knew what the C term ends up being. Okay, that is the ultimate point of the chain rule. And you might want to think back on some of the problems we did in the past that required the chain rule. That same kind of association was trying to be achieved by using that chain rule. Sometimes we use dx, sometimes we use dy. Okay, so that is the reason for that mathematical trick.